Hello everybody and welcome to this tutorial in which we're going to be teaching you, the user, how to find an exoplanet with TESS data. Now, when a planet passes in front of its host star from a certain viewpoint, this can cause the observer to see a dip in the light from the star. So this is a light curve of this star here, and as the planet crosses in front of it, we observe this dip in brightness, and this is called a transit. And from this, we can derive all sorts of information about the planetary system. Now, there are many space missions that have been specifically designed to detect planets using the transit method. One such mission is the Transiting Exoplanet Survey Satellite, or as we like to call it, TESS. You can learn all about TESS through clicking this link here, and this will take you to the guest investigator office for TESS and gives you all sorts of information about the mission and its objectives and the telescope. Now, TESS is a NASA-sponsored Astrophysics Explorer class mission that is performing a near all-sky survey to search for planets transiting nearby stars. The mission observes from a unique elliptical high Earth orbit that provides an unobstructed view of its field to obtain continuous light curves and provides a more stable platform for precise photometry than a low Earth orbit. So this is an artist's illustration of the TESS satellite. And TESS is equipped with 4 CCD cameras that have adjacent fields of view to produce a 4x1 array, or observing sector. And this yields a combined field of view of 26 by 24 degrees, as illustrated below. So this is the 26 by 24 degrees from the 4 CCDs. It's a strip that goes across the sky. Now each hemisphere is split into these observing sectors, and each sector is observed for about 27 days. Now since 2018, when the TESS mission started, it's observed approximately 80% of the sky, mapping both the northern and southern hemispheres and detecting thousands of planetary candidates. Now, data from the TESS mission are publicly available from the MAST archive. And if you click that link, it will take you to the archive as shown here. And if you scroll down and click here, it shows you how to search for objects of interest. It tells you, and you can use this to collect and obtain data. Now, the data from TESS mission come in various forms. And these are full-framed images. These are full sector images with a cadence of about 30 minutes in the years 1 and 2 and 10 minutes in years 3 and 4. There are target pixel files, which are postage stamp cutouts from the FFIs, and these are focused on selected targets of interest. Each stamp has a cadence of 2 minutes or 20 seconds. Or there are light curve files, and these are the time series data produced for each 2-minute or 20-second target pixel file object. So again, we have full-framed images, and you can click on this link and it will give you more information about these. Target pixel files, and you can learn more by clicking this link here, or light curve files. These are the 3 main products that are produced by the TESS mission. To learn more about the TESS mission and its data products, please visit the GI pages that I previously showed. Okay, so the learning goals of this tutorial. In this tutorial, we will teach you, the user, how to access, analyze, and manipulate data from the TESS mission. And this data can also be applied to Kepler and K2, which are the earlier exoplanet missions. We'll be utilizing a Python package called LightCurve. You can learn more about LightCurve from this website. And this offers a user-friendly way to analyze time series data on the brightness of planets, stars, and galaxies. The package is focused on supporting science with Kepler and TESS space telescopes, but can equally be used to analyze light curves obtained by your backyard telescopes. This workshop assumes that you have a basic knowledge of Python and astronomy, and it will walk you, the user, through several concepts outlined below. So, how to use light curve to access the various data products and create time series, how to account for instrumental and noise effects within your data, and how to recover a planet transit from your data. First, we're going to talk about what we need to import to get started. So this tutorial requires the use of some specific packages, LightCurve, Matplotlib, and NumPy. We can import all of these through this cell here. Now this is a Jupyter notebook that I'm using. However, you can take the code that I provide here and put this into your own Python scripts. If you have never used Jupyter Notebooks or Python or complete first-time user, you can actually download this as a Colab notebook. And if you have a Google account, you can run this notebook through Google. All you need to do at the top of this notebook is just install this one line, and that will download the light curve package for you on the server, not to your computer, and you can work through the notebook as we are now. Okay, so first off, we're going to start with how to use light curve to access the various data products and create a time series. You can search the various TESS products using the following light curve functions, so TESS search cut. And again, if you click on each one of these links, it will give you a bit more information from light curve. So search TESS cut, search target pixel file, or search light curve. So these will get you data from the FFIs, these will get you data from the target pixel files, and these will get you the light curve files that you spoke about previously. So in this tutorial, we're going to be examining a nearby bright target, Pi Mansae. Now, around which the star, scientists discovered a short period planet, and this has an orbital period of about 6.27 days. And you can read more about this from this paper here. Okay, so first we want to access the data products. So let's go through each one of the above functions and see what data is available. So again, we're using these functions, we're entering our objects of interest, and we're running through. So it'll take a moment to search for each one of these, and when it is finished, it will produce a table of your results in each case. Okay, so these are the FFI data for our objects of interest. This table here tells you which sector TESS observed it in, what year. This, if you click on it, will give you information about what TESS cut is. There's more information here. This tells you the exposure time of your observations. This is the name of your object. It also tells you that it definitely is your object because it's not further away. And this here just gives you the array index. So we'll note that in sectors 1 through 13 that the cadence of the FFI data is a half hour. But in sectors 27 and above, it's 10 minutes. This is because there was a cadence change from the primary mission, which was years 1 and 2, to the extended mission, which was years 3 and 4. So let's see if there's any other data products, so these target pixel files or light curve files. We can do that by running the following cells. Okay, so there's a whole bunch of TPF data. Some of it are from the SPOC, which is the Science Processing Operations Center at NASA Ames, and some of it will be from the TESS SPOC, and that gives you information about this data product here. There are also higher level science products, but we won't be talking about those in this tutorial. Okay, so our object was observed as a target of interest, and it has both 2-minute and 20-second cadence data. This means that there should be light curve files already in the archive, and so we should be able to check these out. So let's do that. Great. So we can see there's a bunch of data from multiple sectors for our object of interest. Okay, so let's now create a light curve using a light curve file. So for the purposes of this tutorial, we're going to stick with the SPOC data and data which have a 2-minute cadence, and we're only going to return these results. So we can do that by specifying not only the target name, but also the author and the exposure time. This will take just a moment to filter out the results. Okay, great. We can now see that it was observed in these sectors. We've definitely made sure we're asking for the SPOC data, and we're asking only for the 2-minute data. Brilliant. We have 11 search results, so let's download all of these and see what the data looks like. So we can do that by using this download function here, and then we can just see what this looks like. So this tells us that we've got stored in our variable LCF here 11 light curve objects, and it gives you some information about each one, so which sector, the author, the origin. Okay, so now we want to have a look at a specific light curve in a specific sector. So we're going to look at sector 1. So we can do that by specifying the first element of our array. As you can see here, this 0 corresponds to sector 1. So let's run that here. Okay, so this produced a very nice table. This table gives the time, the flux in electrons per second, the error on the flux, any correction in time, the cadence number, and a lot of other information. Now, one thing I want to say here is when you look at this and you look for flux specifically, there's something called SAP flux, and then there's something called PDC SAP flux. Now, I just want to explain what this means. So SAP corresponds to what we see here as simple aperture photometry. The SAP light curve is calculated by summing together the brightness of pixels that fall within an aperture set by the TESS mission. This is often referred to as the optimal aperture, but despite its name, sometimes it can be improved upon. Because the SAP light curve is the sum of brightnesses in a chosen pixel range, it is still subject to artifacts of the mission, so noise and other instrumental effects. The next level above this is what's called the PDC SAP flux, or pre-search data conditioning flux. And this is the SAP flux from which long-term trends have been removed using so-called co-trending basis vectors. And the PDC SAP flux is therefore usually cleaner data and has fewer systematic trends. So for first-time users, this might be what you want to look at, if it's available. Now, when we come to plotting this up, we can switch between what we want to plot up using the following commands. So if we want to specify PDC SAP flux, we can put this. Also note in this case, the default will be this flux, so we don't need to specify it this way. But if we wanted to look at the SAP flux, we could do this here. So let's plot up the PDC SAP and the SAP flux and see what they look like. And we can do that using the following command. Okay, this is the light curve for our object. The SAP is in black. We can see that there are some interesting trends happening here and some dips and divots. And the PDC SAP is much flatter. Okay, so we do want to manipulate these light curves just to pull out our transit. And later on, we're also going to be assessing how, if we only have the SAP flux, how we can remove some of these trends. So for now, let's stick with the PDC SAP and let's try and manipulate this light curve to pull out our transiting exoplanet. So there are a lot of useful functions in light curve that you can apply to work with the data. These include flatten. So again, if you click this link, it will give you more information. And removing outliers. And all sorts of fun things like binning and folding and stuff like that. Now, as I say, we're working with the PDC SAP flux. We're just going to plot this up again by itself. And let's now flatten this to see if we can pull out the transit. There might be some hints here, I'm not sure if you can tell, but let's flatten our data to see if we can do this. Okay, so the light curve now is much flatter. Unfortunately, there's a portion of the light curve that's very noisy due to some jitter in the TESS spacecraft, and we can remove this simply by masking this out. So this is this area here. So let's get rid of this. We can do this by applying a mask. We're defining our mask here, and then we're going to apply it to our light curve that we created earlier. Okay, and we're going to use light curve to plot these two light curves over each other to see and make sure that we've really masked out our bad data. Great, we have. That's great. This looks much better. This is something we can work with now. So let's also try and remove any sort of outliers from our light curve, and we can do this using the function defined here. We're applying that. Okay, things are now getting a little bit cleaner. Can we see if we can see our transit anywhere? Some of you might be able to see it, but again, let's do some more work to pull it out. So one thing we can do is, for this object, we know that the planet C, which is going around, has a period of 6.27 days. So we can use the fold function to find the transit in our data as shown below. So we might be able to see something kind of here. maybe here even. And so what we can do is we can put in our period, we can put in our epoch time, and we can fold around that. So let's try that. Okay, so there's definitely something here going on. Let's see if we can pull this out a little bit more. Maybe we need to bin our data because we have quite a high cadence, and maybe by binning it, it will make it a little bit clearer, and it will also reduce some of the uncertainty in these points that we're seeing. So we can do that by applying the bin function. And now you can see clearly the transit of planet C around our object of interest. It's a beautiful transit that we've been able to pull out. So great, now you found the transit of your first exoplanet. Wonderful. However, what if there isn't any light curve data? What if there isn't any light curve data from the archive available? What if we don't have the PDC SAP flux, but only the SAP flux? How can we pull out the same transit from data that hasn't been as thoroughly processed? Well, you can do this by following the steps outlined below. So we're going to look at sector 1 again. We're going to look at the full frame data, which has a cadence of 30 minutes, and we're going to download this. But remember, the full frame data consists of the entire 96 by 24 sector, and we only want a small region focused around our object of interest. So what we can do is we can say, okay, look at the full frame data from sector 1, but only cut out a small region of 10 by 10 pixels around our object of interest, please. And that's what this is doing here. So this will cut out a small 10 by 10 pixel region around our object of interest. And now we're going to plot it just to make sure that it's actually there. Okay, this is our object of interest. It's definitely there. But now there's no aperture that's been defined for this data that we currently have. So we're going to define it ourselves. So what we can do is we can define an aperture mask, and many decisions go into the choice of aperture mask, including blending and other effects. But in this tutorial, we're going to define an aperture by defining a medium flux value and only selecting pixels at a certain sigma above that threshold. So in most situations, a threshold mask will be the best choice for doing custom aperture photometry. It doesn't involve trial and error beyond finding the best sigma value. So you can define a threshold mask using the following code. So we're saying our threshold is 10. We're going to apply this. It says that there are 18 pixels in this image that meet our threshold requirements. So we're going to plot this up and see what it looks like. Okay, great. There are 18 pixels. It seems like our object is well covered. Brilliant. The next thing to do is sum up the value in those pixels for every single image that we have. So we can do that by using the toLightCurve function. Again, more information is provided if you click on that. And applying our target mask that we previously just defined. And we run that through here. And now we're going to want to plot this up. So this is a table which has all the information, time, flux. Remember, this is SAP flux only. And then this is the light curve that gets produced. Now this looks a bit different from before. There's a lot of scattered data here. There's a lot of things going on where we can't really see any transit. So we're going to really need to filter out and remove some of the noise from this light curve. So again, we're going to apply that mask that we applied previously to get rid of some of this jitter that was going on here. We could do that very similarly to before. Okay, this looks a little bit better, but still there's a lot of scatter and there's maybe some trend, long-term trend happening here. Let's first clip the data, see if we can remove some of the uncertainty. Okay, that helped a little bit, but there is still this long-term trend. So we're going to have to figure out how to remove this. And in this example, to remove this long-term trend, we're going to use one of LightCurve's built-in corrector class functions. And these functions are very useful for removing scattered light and other effects, and you can learn more about them in the set of tutorials that you can find here. Now, specifically for this tutorial, we're going to use pixel level decoloration to remove this long-term trend that we're seeing. And the PLD method has primarily been used to remove systematic trends induced by small spacecraft motions during observations, and has been shown to be successful at improving the precision of data taken by various space telescopes from Spitzer to TESS. PLD works by identifying a set of trends in the pixels surrounding the target star and performing linear regression to create a combination of these trends that effectively models the systematic noise introduced by spacecraft motion. The noise model is then subtracted from the uncorrected light curve, and we can apply that to our data using the code that's shown below. So this is us importing the PLD corrector. This is us applying it to our mask data using the target mass we had already specified above. And we're saying the number of PCA components is 3 because we don't want to overcorrect. And we're going to apply this and see what it looks like. Now, a useful thing here is showing the code is you can do this diagnostic plot. And this will show you the original light curve, a background that gets fitted and removed, and a spline that gets applied. And once those things are applied, you get the light curve as you can see here, which has removed this long trend. Okay, things seem to look a little bit better. So let's again plot this up and see what it looks like. Alright, so the black one here shows the original SAP flux that wasn't corrected, and the blue one shows our corrected SAP flux with the mass that's been applied to remove the jitter. This looks a lot better. So let's now go through the processes that we did before when we had the light curve file object. So we're going to first flatten, okay, and then we're going to fold, and we're going to use the same values from before. So we fold our light curve, and okay, we can kind of make something out here that's very similar to beforehand. It's a little noisier and a bit more difficult to see because of the longer cadence that we have from the FFI data, but there still is something going on here. So let's compare our light curves. Okay, great. So in the black, we have the transit that we derived from the light curve file object data. And in the blue, we now can see the same transit from our FFI data that has been corrected. This is great. The FFI corrected light curve isn't as perfect as the light curve object data, and we can make further adjustments, but for the purpose of this tutorial, this is a good start. So this comes to the end of our tutorial, and we just want to point you to some additional resources. We've shown you the basics of how to obtain, reduce, and analyze TESS data using light curve, and we've only really skimmed the surface. So if you want to learn more about light curve, there is the light curve tutorial page that you can find here. There's also some TESS GI data products page information, which you can find here. It's a set of 7 tutorials that gives you a lot of information. And there are other notebooks that you can find provided by Space Telescope. Once again, I'd like to thank you for your attention. My name is Rebekah Hounsell. I am a support scientist in the TESS Guest Investigator Office. If you have any questions, please feel free to contact us at TESS Help Big Bang, Goddard Space Flight Center, nasa.gov. And thank you very much for your time. Have a good day.